All right, so in this module, I want to go over an example of thermal entropy calculations. And so for this one, we're going to use Al2O3 again, alumina, and we have heat capacity and other data given here on the slide. And what I want you to do is see if you can calculate the entropy content for this material at 900K. So see if you can do that. Pause the video, fill that out on the quiz if there is one. Otherwise, just do this on a piece of scratch paper, and then we will come back and work this one together. All right, so let's go ahead and start taking a look at this thermal entropy calculation. So we're trying to get thermal entropy of Al2O3 at 900K. We're given the heat capacity, so I've reprinted it here. And again, always note on these the range in which it's useful for, so 298 to 1800K. And so we want to go through and make this calculation. And so we need to, again, jot down the entropy equation that we had from the previous module, and that's what we have here. So we have the entropy, the heat capacity data ready to plug in, and we're going to divide that by T and then integrate. And we're integrating from 0, which is our reference point for entropy, up to the temperature of interest. So this is going to be the 900. All right, so one thing you'll notice though is we're going from 0 to T, and you'll notice this data over here actually only goes up or starts at 298, right? That's the standard temperature we always hear about. So we have a 0 to 298 that we have to worry about, right? And so what we can do is we can actually rewrite this. So let's say we want to do the change in entropy for Al2O3 at 900. And so that's going to be from 0 to 900, but what we can actually do, we can actually write this in parts, right? We can write this as 0 to 298 Cp divided by T times dt. So we can basically write this and then add to that 298 to 900, because we can basically add these together, they're additive. And so we basically have just parsed it out. And the reason I did it this way is because this integral right here, this is equal to the standard, so 298, this is equal to the standard state entropy for Al2O3 of formation. So this is what was in the slides as well, this entropy value of formation for Al2O3 at its standard state. And so we can basically plug that in for this quantity, and then we're just left with this calculation, which we can use now because we have information from 298. So this is pretty frequent. Something you'll see is most of the data is only from 298 standard, kind of almost room temperature, whereas this calculation starts at 0. So you have to consider this sort of formation from 0 to 298, and we have that here. So if we do that, if we plug those values in, this first value right here that we see, that was the value that was in the slide as 50.9, and that was in joule per mole for K mole. So that was the value we had. And then when we plug in this other the heat capacity data here, we're going to get basically plugging this in, we're going to get 106.6, and that's going to be 1 over T, because we're dividing by T, plus the second term has a T, so those are going to cancel out, and we basically have a constant. And then the million term down here, 2,850,000. Hopefully I got the right number of zeros there. This is going to be T to the minus 3 now, in that case, and this was all dt. So basically, taking the integral of each term, that's going to leave us with, for 1 over t, this ends up with the log of that. so 106.6 times the natural log of t, but then we evaluate from 298 to 900, so that ends up being 900 over 298. Just plugging everything in. And then the constant term here, when we evaluate that, that becomes multiplied by t, and so we're going to do 0.178, and then multiplied by t2 minus t1, which is 900 minus 298. And then we have one last term, and I'm running out of space, so I'll go down here. So this is the minus 3, t to the minus 3, and so that becomes t to the minus 2 when we evaluate it, and then divided by the minus 2. So we have the constant out front divided by minus 2 times t to the minus 2, and so that's going to be 900 t to the minus 2 minus 298 to the minus 2. All right, so if I kind of go through and plug all those numbers into my calculator, my final value for the entropy here, in this case, is going to be, here I'm going to call it the entropy content for 900. This is equal to 165.2, and this is joules per mole K, which is the same unit as the heat capacity as well as the unit here. So all those units match up. This is joules per mole. This is joules per mole K. And so this is our kind of final answer here. And again, I didn't put the delta sign here because we have it in terms of the reference value of formation here. So that takes care of the entropy. So we can just kind of refer to it as entropy content at a given temperature instead of the delta. So that is how we can use, again, heat capacity to calculate thermal entropy for a given material and temperature reference point.